Okay, next let us continue the third part of today's class. Okay, in the end of the second part, okay, we know that this equation is equal to the expectation of z minus, okay, z minus the expectation of z times z minus the expectation of z transpose, and which is equal to r zz. Okay, like this, and this is equal to above a. Okay. Okay, we call this equality A. Okay, sigma square times I n r. Okay, and this is equation 18. And let me align at the equality sign. Oh, so I can align it. Okay. Okay, I can't align it. So this should be I boldface. Okay, INR. Okay, where are ZZ? Is the covariance matrix of Z, and equality A results from equation 2.24. Okay, let us see equation 2.24. Okay, equation 2.24. Okay, this equation RZZ is equal to sigma squared times INR. Okay, finally, substituting equations 13, 16, 17, and 18 into equation 2, we get. Okay, let us go see equation 13. Okay, equation 13, H times the expectation of S times S transpose times H transpose is equal to H times RSS times H transpose. And equation 16. Okay, in equation 16, the expectation of H times S times Z transpose is equal to 0. And 17, in equation 17, the expectation of V times H transpose times H transpose is equal to 0. And 18, okay, in equation 18, the expectation of V times Z transpose is equal to sigma square INR. Into equation 2, okay, equation 2. In equation 2, we can see that it is equal to the expectation of these 4 terms. Okay, we get, equation 2 is equal to, first, this term, H times R SS times H transpose plus this term, equation 19. So we have finished the solution of this problem. Do you have any questions? If you do not have any questions, let us go back to the slides. And please turn to page 100. So finally we can get the equation 2.13, 30, which is equal to H times RSS times H transpose plus sigma square times INR. Substituting this expression for RRR into equation 2.29. In equation 2.29, the maximum of H of R, that is the entropy of R, where R is the received signal vector, is equal to NR over 2, where NR is the number of received antennas, times log 2 of 2 pi e plus 1 over 2 times log 2 of the determinant of RRR bits. So yields the maximum of H of R is equal to NR over 2 times log 2 2 pi e plus 1 over 2 times log 2 the determinant of H times RSS times H transpose plus sigma square times INR bits. Next, let us go to section 2.8, final result. First let us see the case, section 2.8.1, real signals. Since our discussion thus far has specifically focused on real signals only, we first develop the capacity expression for real signals, then generalize to complex signals. The minimal capacity of a real signal, C real, is obtained by substituting equation 2.27. Let us see equation 2.27. Where H of Z and Z is the noise vector is equal to NR over 2 times log 2 of 2 pi e plus 1 over 2 times log 2 of the determinant of sigma square times INR. Back to the slides. And equation 2.31, Okay, let us see equation 2.31. Okay, this is the equation we have seen about several minutes ago. Okay, into equation 2.21. Okay, in equation 2.21, C MIMO, that is the MIMO capacity, is equal to the maximum of H of R minus H of V. And the X maximum is taken over all possible PS of S1 to SNT. Okay, where S1 to SNT are the transmitted symbols on the first to NT's transmit antenna, and S is the transmitted symbol vector. Okay. So let us go back to the slides. Okay, resulting in the following. Okay, first we know that C real is equal to the maximum of H of R minus H of V. And this equation is equal to 1 over 2 times log 2 of the determinant of H times RSS times H transpose plus sigma square times I minus 1 over 2 times log 2 of the determinant of sigma square times I. Okay, how to derive this equality? Let us see the blackboard. Okay, because I do not have a blackboard now, I use the Microsoft Word instead. Okay, this is chapter 2, page 104, problem 1. Okay, derive the second equality in equation 2.32. Okay, this boldface. Okay, solution from equation 2.27. We know that. Okay, solution boldface. Okay, we know that. Okay, let us see equation 2.27. Okay, we know that this equation. Okay, copy and paste. And this is equation 1. Okay, we know that H of V is equal to NR over 2 times log 2 of 2 pi E plus 1 over 2 times log 2 of the determinant of sigma square times INR. Okay, next from equation 2.31. We know that. Okay, let us go to equation 2.31. Okay, is this equation. Okay, we know that the maximum of HR. Okay, let me combine into one line. Okay. Oh, sorry. I can combine this into one line. So this is equation 2. Oh, equation 2. Okay, equation 2. Okay, so the maximum of h of r, okay, r should not be italic, is equal to nr over 2 times log 2 of 2 pi e plus 1 over 2 times log 2 of the determinant of h times RSS times h transpose plus sigma squared times INR bits. Okay, because h of v is a constant. Okay, we can see that in the equation 1, h of v is a constant. That is, we do not have any random variable or random vector or random matrix here. Okay, so the maxima. Okay, maxima of h of r minus h of v okay, so I need a okay, oh sorry, so I need a minus sign here. Okay, how can I have a minus sign here? Okay, let us see, minus sign. Okay, sorry, I can't. Okay, minus. Okay, sorry, this actually this is the heaven, not the minus sign. Okay, which is equal to the maxima of h of r, okay, minus h of v. Okay, okay, because h of v is a constant, so we can move h of v out of the maxima. And this is equal to, okay, h of r is equal to this term. Oh, and plus this term. And minus, okay, this term. And minus this term. Okay, like this. Okay, so this is equal to, okay, we can see that this term and this term can be cancelled. So this is equal to the second term. Okay, plus the last term here. Okay. Okay, so let me align at the equality sign. Okay, like this. And I add a white equality sign here. Okay. Okay, like this. Okay, so this is the equation 3. Oh, I can't align it. Okay, equation 3. So we have finished solve the this problem. Do you have any questions? Okay. So if you do not have any questions, let us go back to. Oh, sorry, I need to save this file. Okay, chapter 2, page 104, problem 1. Okay, and save to the blackboard of Mimo. Okay, so let us go back to the slides. So we have, okay, let us change the pointer. So we have derived this equation. And according to a property of the log function, okay, log 2 of x minus log 2 of y is equal to log 2 of x over y. Okay, so simply we can get this equation. Then this equation is equal to this equation. Okay, we can see that in the denominator, the determinant of sigma squared times I is equal to the sigma to the power of 2nr times the determinant of I. Okay, so let us see how to derive this equality. Okay, let us see the blackboard. Okay, again, because I do not have a blackboard now. Okay, so I use the Microsoft Word instead. Okay, this is chapter 2, page 104, problem 2. Derive the fourth equality in equation 2.32. Okay, this is problem 2. And this is the solution. Okay, in matrix property, okay, this should be boldface. Okay, 1.99.2 dash G. We know that. Okay, let us see matrix property 1.9.2-G. Okay, please open the slides of chapter 1 and turn to the page. Okay, 231. Okay, let change the pointer. Let capital A and capital B denote any two matrices having the same dimensions n by n, and small a denote any non-zero scalar. Then 1 over a to the power of n times the determinant of a plus b, capital A plus capital B is equal to the determinant of capital A over small a plus capital B over small a. Okay, so let us go back to Word. Okay, we know that 1 over a to the power of n. Okay, sorry. Okay. I can't. So over. Let us insert a fraction. 1 over a to the power of n, and the determinant, okay, of a plus b is equal to the determinant of capital A. So it is 25 minutes. See you next time. Goodbye.